Hey y'all, thanks for attending. I'm Randall, and I'm the lead ML engineer here at Labelbox. First off, a little bit about myself. My ML experience is largely in adapting and training transformer-based models for large data sets on the order of hundreds of millions of examples for NLP problems. And what I found in my experience is that training large models on large data sets usually creates a few problems. Having to work with distributed GPUs or specialized hardware like TPUs, or having to figure out how to run expensive experiments to validate that your model architecture changes do in fact improve model performance, or maybe your increase in data set does improve model performance. And then last but definitely not the least of all, figuring out how to get all that data labeled. When you have large data sets that only increase day after day, how do you manage this immense cost of labeling? Um, However, before we decide to just get more data and label it, let's understand when we should do that. So today we're here to talk about how much training data you really need to build a performant deep learning model. But first off, we should figure out and understand the various ways we can improve model performance. Um, when using deep learning, once you've built a proof of concept in some throwaway Jupyter notebook and want to start doing real engineering work to make your model performant at scale, it is often unclear how we should exactly scale our approach and how we chase that performance. Furthermore, if we choose to train with more and more data, it is unclear how much we actually need. So after we talk about how we improve model performance, we will focus on how larger data sets can help model performance. And we will be framing our discussion using this paper, Deep Learning Scaling is Predictable Empirically, and it'll help us build some intuition around this. And then, of course, we'll discuss how Labelbox fits into all of this. So let's get started. There are, in general, three ways to improve model performance. And the first way we will talk about is improving your model architecture. This is probably the flashiest, the one you read the most about. This is where papers get published. And we've seen many great breakthroughs in this category. Usually these breakthroughs come from ML researchers and require a fairly deep mathematical or computational background and deep understanding of prior work in model architectures. And inspiration for these can come from a variety of fields. And so one way that model architecture helps is that it can make your model more compute optimized. And by that, I mean the model is built in such a way that it takes advantage of existing hardware and makes training fast. One of the older examples of compute optimized improvements to model architecture, as many of you may know, is our CNNs, convolutional neural networks. And they were inspired by local receptive fields inside the human brain. And not only do these have a biological basis, they're also very straightforward to calculate using a GPU. Just simply a matter of matrix multiplication. A more recent innovation would be transformers, which solve several compute bottlenecks for maintaining context, especially in NLP. I won't go into deep details here, but the self-attention component is also a simple matrix multiplication and allows every word in the context to be computed in parallel rather than in serial. And so you can see it's optimized for these GPUs that have already existed. Another way for model architecture changes to increase your model performance is to just extend the model context, right? Your model needs to attend to different parts of your example and be able to hold all of that state while it's deciding what the prediction is. An older innovation here, as an example, would just be RNNs, recurrent neural networks. And these are built to take advantage of the fact that text has long-range dependencies. And so you would be keeping track of state across the entire piece of text that you read. But of course, by extending model context here, it does come at some cost to compute. And this is, RNNs are fairly expensive to compute. but it does get you that global context. We'll talk about transformers again. This is like I said, this is a more modern innovation, but instead of taking into account words that are far away by serially processing them, we can do it in parallel. And transformers are able to extend model context this way and take into account all the words in the example if necessary. However, this does also come at a cost to your model size. So for example, if you have 1,000 tokens you are feeding in, it's going to make your model 1,000 squared in terms of weights for the self-attention matrix. Another innovation would be the reformer, which was just an extension to the transformer, and this addresses that quadratic scaling of the model size, allowing longer context without the model size scaling quite so drastically. Another example of how to improve model architecture would just be to enable larger model capacity. The more parameters you have in general in the long term, the more it can generalize and learn from more data. There are obviously caveats to this, such as like the double descent phenomenon, but on a large enough scale, it is true that the larger the model, the better, especially if you have a lot of data. One innovation that allowed larger models is ResNet, which employed skip connections to speed up training, allowing practitioners to increase model size without training taking as long as it would have. Another innovation is mixed precision. It turns out you don't actually need the full 32-bit precision for the floats that describe your model's weights. And if you use, say, half of that, 16-bit precision or less, you don't actually see a big hit to model performance. And with less precision, whatever hardware you're training your model on can fit either nearly twice as much data or a model that is twice as large. And so that'll get you better performance for, very minimal hit to baseline performance. So yeah, there was a whirlwind through, historically some ways that improving model architecture have improved model performance. And so we'll talk about another way to increase performance, which is through just simply scaling your compute. And in general, by getting more compute, you can increase model capacity, you can speed up training, and you can show the model more data for every training step. And in general, those are all good things. And so how does this happen? How do we train larger models faster with more data? One way is just to use dedicated chips. This is probably the earliest innovation, is people realized GPUs were already built to do matrix multiplication very fast. And so the GPU is an example of like a dedicated chip, or the TPU, which is architected specifically to handle data I/O for machine learning, and also dedicated to processing very machine learning specific operations. Another way is just to use larger machines. So if you've looked at TPUs before, year over year, they keep increasing in size. You can see here that, version 3 goes up to 2048 pods or cores, and they hold 32 terabytes of memory. And that's immense, right? And so always using larger machines, you can always just fit more of your model, more data onto your model. Another way is to do distributed training. And so if you can't find a larger machine, one way is to just use multiple machines. You can see here, there are two ways to take advantage of multiple machines. You can split your model across the machines, or you can have the same model on all machines and just split up the amount of the batches of data across your machines. And this will let you, of course, train faster, train larger models with more data. And so we've seen these two ways to improve model performance. The last way that we will talk about is just simply to get more data, to curate larger data sets. And this can come in the form of a larger breadth of examples, exposing your model to more input and output modalities, or just sheer number of examples. One way, like I said, is to just label more examples for training. And the more of this you have, your model will understand your problem better, more of your problem. You can also just gather rare examples. Maybe you already know from looking at your model performance that it doesn't do well on certain rare examples, where it's never seen certain examples in its training set. Go ahead and go find those examples. Deal with edge cases, and this will which will let your model generalize better. And one sort of like heuristic here is like we know from historically that ImageNet was pretty much the one thing that unlocked most of the advances we see now in deep learning. And that was impossible without collecting a data set that was the size of ImageNet, 14 million images with 20,000 classes, and everything sort of trickled down from this. And so one way to think about this is you have your business use case, you have your specific domain, whether it's agricultural, medical, otherwise. And so the open question really is, what will be the ImageNet for your domain, and how are you going to get there? And so now that we've seen that there are a few ways to improve model performance, how do we evaluate the trade-offs, right? We remember that by improving model architecture, we can get a model that generalizes better, trains faster, sees more data per step. We know that scaling compute can also train faster and get your model to see more data per step. And curating large data sets will help your model generalize and deal with rare examples better. And so now that we understand all three, how do we choose between them, right? How do we decide where to spend our resources, precious engineering resources? And so let's consider sort of the trade-off between speed, performance, R&D, and engineering. And so I think what we find is that in general, improving model architecture is a deep R&D problem that is typically best left to PhDs, or you can adopt from research papers, and usually gets you both performance gains and speed. And so that lies somewhere here on the quadrants. We find that typically scaling compute is both an engineering and R&D problem, and that it gets you mostly speed and some performance gain. What we find with curating larger data sets is that it squarely falls in the engineering effort, right? How do I get this data labeled? How do I find all this data? How do I, push it around? And not only is it mostly an entire engineering effort, it also mostly benefits performance. And so we will be focusing on this lever for improving model performance. And to focus, the most important thing to understand here, if we choose to go down this route of curating larger data sets in order to improve our model, we need to understand the exact impact that a larger training data set will have on our model performance. So let's go through a few empirical examples. So here we see a graph that shows the results of training many models over differently sized data sets. Keep in mind that the two axes here, the Y and the X axes, are both log scale. So you can see that the Y axis shows our model performance as measured by loss on our test split. Keep in mind, the lower the loss is, the more performant the model is. And on the X axis, we see also log scale for data set size in terms of number of tokens. And this example that we're going through is a neural machine translation example. And so tokens is how we measure the amount of data the model sees. And you can see that it is X-axis is log scale, as we mentioned. Every interval is twice as many tokens as the previous interval. And to be clear here, a linear curve that we see denotes a logarithmic improvement. And so basically it gets harder with every step. And so we see that for translation problems, models will in general follow the traditional logarithmic gains in performance as a function of logarithmic increase in data set size. In other words, you're going to need twice as much data for each diminishing incremental unit of model performance gain. And we see that this relationship is fairly reliable until we get to very good performance, at which point it takes much more than just twice the amount of data for each marginal performance increase. Cool. So let's look at also language models, training language models. We see the same thing here. Although for this experiment, we are using older school recurrent networks rather than more modern transformer-based models. But we can see that we have the same logarithmic relationship where it takes exponentially more data to obtain smaller and smaller improvements to model performance. And for image classification, we see a fairly similar relationship with a minor difference. We see that we only start to get performance gains after a certain amount of data. So you can see here that the loss does not decrease until you get to around 8 images per class. And then from there, you start hitting your stride with a logarithmic increase. Yeah, once we start improving, the improvement there again is logarithmic. And so we can generalize these relationships as a curve that roughly looks like this. And we can also characterize the various regimes we encounter as we go through this process. So first, we start trying to do better than a model that is just randomly guessing for its predictions. And we see that, we can call that the small data region. For example, when we looked at the image classification example, under 8 examples per class would be squarely inside the small data region, as we don't really hit the logarithmic improvement. And then once we're out of that, we start hitting this power law region where we quickly enter this power law region where model performance requires increasingly more and more data. And eventually we enter the irreducible error region where there are fundamental reasons for why we can't do better. And in practice though, this region has not been entered for most problems. So if you're not training over MNIST, you're almost certainly just exiting the small data region and trying to work your way slowly down the long and increasingly steep power law region. And this region, the power law region, is the most important because we face exponentially increasing costs and around data acquisition and labeling. And so let's look at how labeling costs scale in this power law region. You may recall, if you look, were attending the last webcast, that we know that for every additional piece of data we annotate, we will need to pay a labeling cost. And so there's a linear relationship between the two. However, as we just showed, model performance usually has diminishing returns as a function of the number of examples the model sees during training time. So this is the logarithmic relationship we were describing earlier. This leads to a less than ideal logarithmic relationship between model performance and labeling cost. And so even with, say, transfer learning, you can often achieve 80% performance with just several hundred examples. However, due to the long tail nature of many data distributions and this logarithmic power law region, the next 10% will probably require thousands of examples. And the next 5% will probably require tens of thousands. And so you get this, increase in cost. So what do we do about this, right? So what we believe here at Labelbox is that model-assisted labeling provides you with crucial assistance in the power law region. And how does model-assisted labeling work, right? It's very easy. All you do is you hop into Labelbox, you generate annotations with whatever V0 of your model you have. You upload them to Labelbox using the Python SDK, and then you start labeling. And your labeler should see those model predictions, and that should speed up the labeling process. So let's see how that affects your cost, right? How does this cut your labeling costs? As we recall, labeling efforts scale linearly with a number of human annotations, and model performance scales logarithmically with labeling costs. And in the ML ecosystem, there are typically many editor tools, including, our nice editor that sort of just makes the experience smoother and faster. And this should lower your labeling costs a little bit, right? And this will get you some cost savings per label and thus some cost savings for training your model. However, only your model is domain specific and trained on your data set. These editor tools don't really know anything about your problem. They sort of rely on general heuristics or good UX to push that labeling cost. And so your data and your model are typically what set you apart from your competitors and will be much more performant than any general model off the shelf that is trained on a generic data set. And only your model will keep improving over time. And so here we can see that if we take advantage of your model as it improves, we can see that if we use, say, version 0 of your model, we're going to be reducing costs, labeling costs, and this will be improving model performance per cost. And if we keep doing this with better versions of your model as you keep retraining, we're going to keep cutting our labeling costs. And so this can keep going as, you know, machine learning development is not a one and done situation. Machine learning engineers are always looking for ways to improve model performance, as we went through. And as they do, you're going to keep reaping these benefits, driving your labeling costs even lower. And so if we pull everything that we learned today together, how do we know when to start using model-assisted labeling? So as with anything machine learning related, we should put on our scientist hats and experiment. But one way to know when you're ready to start is your model is better than random guess, and your model has exited that small data region that we talked about, and you're squarely in that power law region. And so we can use Labelbox to see if this is true by just looking at, see if we cover rare examples sufficiently, see if we covered the general cases sufficiently. You can hop in Labelbox, see what makes up your data set. And then, like I said, we should be measuring. If we're experimenting, we should be measuring. And so another way, once we start using model-assisted labeling, we should be tracking how it's affecting our labeling costs. And you can use Labelbox to track labeler performance before and after model-assisted labeling. You can look at how much time they take on every label. And yeah, the important thing here is to experiment with different models, whether it's the model you're training, other models that are related to your problem that you think can help your labelers label faster and more accurately, and see if it helps. And because of how easy it is to use model-assisted labeling, you should not be afraid to just try something that seems promising. And then as long as you're measuring labeler performance, you'll know if it is. And so, yeah, we have seen that model-assisted labeling can be extremely useful in increasing model performance. And it's one of the many levers for improving model performance, and probably the most engineering focused and also performance focused lever. And this is all part of what our training data platform looks like, letting you manage your workforce and workflows, annotate your data, and most importantly, iterate by including your ever improving model in this process. Great, so thanks for listening. And now we'll be taking questions.
Great, thank you, Randall. And this is David from the Labelbox team here. I'll be moderating the Q&A. Tons of great questions so far, and keep them coming. We want to have an interactive conversation about what we just discussed, clarify anything that may not have been covered as deeply as you'd like, and we can get this started first here. First question here for you, Randall. How do you know if you have too much data? Is there such a thing?
Sorry, I was muted. Yeah, so that's a tough question, but in general, I would say that's not really a thing. Obviously, there's more informative data for your model, and there's less informative data for your model, and you can always prioritize which ones of these get labeled through our queue prioritization API. But yeah, in general, you don't need to turn it down. The only question is, should you get it labeled? And in general, more is almost always better for model performance past a certain point. And though do keep in mind that your business use case may not require great model performance, right? Like you may be able to reach that 80% and maybe your business use case is achieved that way. Though do keep in mind that models do have to be maintained and retrained on ever-changing data. So the input distribution that your model sees today may not be the same input distribution that it sees, say, a quarter from now. And so you're always going to be in this battle of maintaining your model. And so in that case, like your steady stream of data coming in to maintain your model is, that's important to get labeled and feedback into retraining your model. So yeah, complicated answer, but in general, I would say it's not really a bad thing.
Yeah. Next question here from Nathan. You mentioned several criteria about improving model performance, but didn't talk about loss criteria. Would you just consider that part of model architecture improvement?
Yeah, I guess to take a step back here, there are many ways to measure model performance. So probably the thing that's closest to the math is the loss, and that's exactly what the model is. Your optimizer is going to be optimizing for. And so that's the realist measure of if your model is improving. But the closest to the business use case measure is typically your validation metrics. So accuracy, precision recall, whatever other metrics you have that are actually tied closer to the business use case. So I would encourage also using those to keep track. Like your optimizer could go to 0, but you may not have solved your business use case. And so in the graphs I showed, we focused on loss because that's just closest to the behavior of models in general. But if you're addressing a business use case, make sure you have good validation metrics that are not just loss, right? Loss does not translate to business requirements. And so, yeah, I would keep track of both.
Next question here. Are there good ways to figure out which data to prioritize labeling first for the best model performance?
Yeah, so one of the simplest ways to do that is just to let your model tell you. In most, depending on your model architecture, it may have a way for you to extract model uncertainty. So your model can tell you with every example it sees, is it confident that this is a prediction? And if you just prioritize all the examples that your model is not confident on, that's a great way for the model to tell you exactly what data you should prioritize. And so if you run your existing model over unlabeled data, you see that it's not confident on a subset, I would prioritize that subset. And there are more complicated ways to address this, but that's the general philosophy.
Next question from Chris. How does active learning play into intelligent label selection? Do you see big impacts from active learning in production systems?
Yeah, so I mean, I think that ties exactly to my previous answer. And I believe it's very important, especially if you already sort of tapped out on the amount of data you can get labeled. Yes, definitely use active learning, definitely come up with ways to figure out what data is more important for your model to see next. And like I said, using the model's own confidence is one way. Another way is maybe you already know from a business perspective, like, hey, here's a rare example. I saw the model fail on this. Okay, let's use human intuition, go find more examples that look like that. That's another way to be very heavy-handed about active learning versus sort of let the model automatically tell you. And so, yeah, for sure, active learning is going to be super important, especially if you're very, very concerned with picking out the best pieces of data for you to look at. But that's only important after a certain volume of data, right? Like you can, with today's technology, you can very easily train a model on tens of thousands of examples without breaking a sweat. So I would not really worry about that until you're sort of out of that small data region and you're well into the power law region.
Thanks, Randall. We have a few questions about this next topic, so maybe I'll just paraphrase it and you can answer it generally and then dive deeper if needed. How can we ensure that labels generated and labeled using model-assisted labeling do not confirm model biases?
Yeah, so that's a good question. So, I mean, Labelbox has several tools, benchmarks and consensus for making sure that your labelers are, performing as you expect them to. And so that's definitely one toolbox you can use. Another is just to keep track of how long they're taking, right? And also, like, you need to understand your problem to know how your model assisted labeling is going to be helping your labelers, right? You can have the model only output areas that it's uncertain on, and then have people correct that. Or you can have your model output areas that you don't want your labelers to focus on, and then have them focus on more important areas. And so like I said, like that experimentation is super important part of this process, and which is why we've made the integration process so simple. Again, you need to, you need to understand where your labeler is struggling and where they're not struggling, and where they are struggling, help them out. That would be my answer.
Yeah, if you're interested also in learning more about Labelbox's QA tools, feel free to check out our documentation on our website. We have specific sections on benchmarks, consensus, gold standard. Next question here from Nils. How do you see synthetic data helping to beat the power law versus label data?
Yeah, that's a good question. So synthetic data will probably help you, but in general, in general, synthetic data it's difficult to make sure your synthetic data matches your input distribution from the real world on all dimensions. You can understand your problem very closely and realize like, hey, I don't really care if it matches the distribution on, say, these dimensions, and I'm okay taking that, biasing my model towards a fake reality for those dimensions, and then getting the gains from having much more data in this dimension. And that's sort of how you need to think about synthetic data. And obviously, again, experimentation fits into this again. Like if you generate a bunch of synthetic data and you train your model, and it just like the model gets better on the training set, but it just crashes, does terribly on the test set, then you know your synthetic data is steering it in the wrong direction. And so that's like a big fear with synthetic data. And then label data, you sort of a priori assume that it comes from the real world. And so you sort of get less of that concern. And so it's this trade-off between the cost of synthetic data and the quality of it versus the cost of labeling data and the quality of it. And so, yeah, experiment as always, and keep those two trade-offs in mind.
Great. Next question here from Tambit. How do you understand that most of your data is too homogeneous and just wasting your training cycles? That you would achieve the same performance with much less data?
Yeah, so this is a good question. I think it fits back to our discussion about active learning. Yeah, there's definitely a concern. To address it, you should use active learning, right? Find data that is most useful to show your model next. As for your question to how to figure this, like see if this is happening, you're just going to have good validation metrics along the way while you're training, right? Make sure for however many training steps, you have your evaluation period. And then during this evaluation period, if you see that you're not improving for certain parts of the epoch, maybe you do curriculum learning so that you know which parts of the epoch is which kind of data within reason. Then you can very easily pinpoint sort of like where what subsets of the data set is not super informative. Though in general, you need to be careful there, of course, because you do want to keep your batches relatively similar in distribution. So you're going to be shuffling your whole training set. But that would be one way you can quickly experiment and see like, hey, if I took this model, I trained it on this subset of data and it doesn't do anything, it does very little, like likely that's going to be, less informative. But the easier way to do this is just use active learning once you get to that point where you really care about the amount of keeping the amount of data minimal.
Next question here, two-part question from Julian. What's your stance on retraining frequency? How do you compare different model seasons, parentheses, same model trained on newer data? Would you keep the test set constant or not?
Yeah, good question. I think this ties back to, having deep conversation with your product manager or whatever, whoever is in charge of ensuring that business requirements are met. So in general, I can give you a few, I guess, like heuristics here. But if you find that there is clear seasonality in your data, you're going to want to at least follow that for either maintaining separate models, say for the fall versus for the spring. Or you can follow that seasonality and just retrain, say, every quarter, right? There's always going to be a trade-off here, right? How much drift can you allow your model in production to have compared to the data that it's seeing in production versus the cost of training, right? So if your cost of retraining is very low, then yeah, sure, let's do this every day or every sprint, right? But if it's higher, then you want to trade that off against how fast your input data is changing. And so what's important here is having good monitoring on your model that is in production and seeing, hey, is the input distribution what I expect? Is the output distribution what I expect? And where's the threshold for, like, if those distributions are this far away, like, okay, we're starting to miss some business requirements. We have to eat that cost of retraining. And so, yeah, take a very metrics driven approach here because, yeah, retraining is expensive, especially at the scale that most people work, on these days.
Great. Next question here from Kenneth. How would you go about flagging, handling, quote unquote, contaminated or incorrectly labeled data at a large scale?
Yeah, that's a good question. So I assume kind of like if there's contaminated data, you already have a way of picking that out. So that should be part of any sort of like correctness tests in your pipeline, right? Like if the distribution changes beyond a certain point, raise a flag, drop that piece of data, go look at it afterwards. If you don't have a way to tell, then you need to come up with a way, right? There are easy ways, just like check the distribution if it's drifting. Maybe you understand from a business perspective, like, oh, this is something that labelers always have trouble with. Put in checks for basically tests inside your pipeline to check for those cases, and then figure out a way to work with whoever's managing your labeling workforce and figure out how to maybe use like benchmarks and consensus to prevent that from happening in the future. Yeah.
Next question from Sebastian here. Can I integrate labeling outsourcing service providers? The answer is yes, Sebastian, but Randall, feel free to add context to that as well.
Yeah, no, I think that's a simple answer. It's just yes. Yeah.
Great. Let's see. Next question. Are there ways that you've seen for smaller companies to get an edge when it comes to data sets, or will the larger incumbents typically have a data advantage?
Yeah, this is a good question. So data can be acquired in many ways. And there are many specific domains where data can create a moat that large incumbents are not aware of or interested in. So for example, if you have a unique assembly line that you're trying to put include a model in, or relationships with customers that have unique assembly lines, like Facebook, for example, will never in all likelihood have that data, right? So lean into your unique relationships, your unique data, and that's typically what you see a lot of these smaller companies do. And obviously you can see if maybe you have more clever approaches for getting data than these companies, right? Because you may not have an existing pipeline for you to just get data day after day. Maybe there are interesting data partnerships you can have, create with clients, or maybe there are, public data sets you can use, or maybe there are ways you can use weak labeling to generate better labels on like extremely large data sets that just, other people have not labeled. So yeah, there are definitely a few clever ways to do this. But I would say the long tail of applications of machine learning is very, very, there's a lot of ripe areas for the picking. Yeah.
Great. I think we have time for a few more questions, and then we'll likely wrap up the session for today here. See, Labelbox, is there a pricing structure for image, video, text labeling? The question is regarding pricing in general, but I would say, yes, we do have specific packages for combining images and video and even text. So reach out to our sales team, and we're happy to tell you more and go into details based on your specific use case here. Next question. Do you see the cost of distributed computing continue to decrease?
Yeah, in my opinion, I think definitely. The speed at which GPU and TPU power and memory and size has increased, the speed at which they have increased is, astounding. And the ease of using distributed training is the primary focus now of a lot of popular frameworks. I think TensorFlow is reaching the end of its growing pains around helping you do distributed training. It used to be extremely, extremely hairy, but now it's much easier. And yeah, other frameworks are definitely addressing that same problem. And then I think there are a lot of newer sort of data platforms that try to address like how do you do distributed training. And so yeah, I think the costs are just going to keep decreasing as compute in general does.
Great. This is a very specific question from John here, but can Labelbox use my ONNX model for model assisted labeling?
Right. So we don't take your models directly. We just take the outputs of your model. We don't, if you're going to be building a model and you're going to have it in production, you're going to be running it already in inference. And so just feed us that. And in addition to producing your predictions from your model for your business use case or for your own validation, feed it along back to Labelbox for improving the labeling process. And so, yeah, we don't host, we don't deploy, we don't run for you. We assume you already have that because that's sort of part of the table stakes. And so all you need to do is upload the outputs of your model. So short answer is no, but yeah.
Great. One more question here. Which methodology is best for semantic segmentation? Matterport, Mask, RCNN, or Detectron?
Sorry, read that again. I'm trying to find it in this list.
Yeah, which methodology is best for semantic segmentation? For instance, like Matterport, Mask, RCNN, or Detectron?
Yeah, I mean, this entirely depends on your problem, right? Like as I understand, Mask RCNN is a little older, and then Detectron is a little newer. I believe Detectron, just off the top of my head, I think it trains faster. And I think for most benchmarks, it did have better performance than Mask RCNN. But yeah, I mean, obviously just go take a look at the original papers that produced them, see their benchmarks, swap the two out for your problem, check which one does better. Like, again, like experimentation is king here. You should build your machine learning pipeline in such a way that you can just easily swap in and swap out model architectures, and thus sort of figure out which one's the best. But yeah, if you can't do that, just go look at the paper and see like its performance on benchmarks. I recall Detectron 2 just does better. So that's a good one to start with.
Thank you, Randall. And I wanted to thank all the attendees for joining us today. We really enjoyed our conversation here, and thanks for all the great questions. We'll be putting on another session in a few weeks, so please stay tuned for any updates there. And thank you very much again.